Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible. We would also greatly appreciate if you consider supporting us as well. So click the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a simple yet quite important topic in regression modeling and econometrics, which is functional forms in ordinary least squares regression modeling. It is quite common in econometrics to transform your data before you run estimations with it to achieve a better fit and to represent the nature of your data more accurately. And one of the most common such transformations is to take natural logarithms of either your independent variable, your dependent variable, or both. And today we're discussing the concept behind why taking logarithms sometimes works so well, when it does not work so well, and how to interpret the results of different models that emerge when you logarithmically transform either the dependent variable, your y, your independent variable, x, or both. And we will approach it from a quite simple example motivated by macroeconomics, which is we'll investigate the relationship between capital per worker and labor productivity. Basically, how well do people across countries utilize their capital endowments? And we have got data on real GDP, population, and capital stock for a list of 180 countries, and all of them are in million, either million people or $1 million. To run our simple linear regression and transformations thereof, we need to calculate GDP per capita and capital per worker. Again, here we simplify, we just assume that we have got an adjustment for every person, not for every worker. That simplifies it quite a bit, but keep that in mind. So we calculate GDP per capita, our proxy of labor productivity, by dividing real GDP in $1 million by population in million people, and that gives us real GDP per capita in dollars per person. So for example, in Aruba, it's $32,614 per person. If we bottom right click it all the way down, we get GDP per capita for all of our sample countries. And capital per worker, well, we just divide capital stock in $1 million by population in million people. And we see that, for example, Aruba, having a capital endowment of $173,000 per person, produces around $33,000 worth of goods per person again. Whereas for Angola, for example, both of those figures are lower. So again, we might want to model some relationship between how much capital there exists per person and how much stuff is being produced per person. And obviously the easiest approach would be to use a linear form or a lin-lin equation, which is basically GDP per capita equals A plus B times capital per worker. This allows us to model unit changes in X, or our independent variable, our capital per worker, leading to unit changes in Y, or our GDP per capita. So basically, every additional dollar of capital per worker leads to B dollars of GDP per capita being additionally produced. So if we estimate the linear model, we can just use the linest function, plug in our linear GDP per capita, so not transformed, and our capital per worker, not transformed, one for the constant, one for the additional statistics, and enforce the model. And we see that our slope is 0.18, meaning that an additional dollar worth of capital per worker leads to 18 cents of GDP per capita being produced additionally. The constant here is being interpreted as the value of GDP per capita if our independent variable, our capital per worker, is 0. So basically, even if there is no capital whatsoever, people would still produce some valuable stuff, which is how you can interpret this coefficient being positive. And again, this is how you can interpret further significance testing that we'll undertake. What is also crucial here is that the R squared is 0.87, which means that variations in capital per worker, if we assume that the relationship is linear, explains 87% in variation of GDP per capita. So basically having capital is quite important in producing stuff, which is perhaps intuitive and not at all surprising. However, is it the best functional relationship we can use to model the tendency of countries with higher capital endowments being richer? Well, for that, we just have to take natural logarithms of GDP per capita and of capital per worker and enforce it throughout our sample. And now we can consider the alternative functional form specifications that make use of logarithmically transformed variables. The first one is the exponential regression, or a log-lin form, where you take the logarithm of y but do not take the logarithm of x. You leave x to be linear. Why is it called an exponential regression? Well, here we are modeling the logarithm of y, not y itself. So if we want to express y in terms of x, it is an exponential function. It's the exponent of the constant times the exponent of bx. That allows us to interpret the result as follows. Unit changes in x, our independent variable, in that case capital per worker, lead to a relative change or a percentage change in y, or our dependent variable, GDP per capita. Basically, every additional dollar of capital per worker will increase the GDP per capita not by some unit, but by a factor of something, or by some amount of times, or by some percentage. That allows us to model relationships that are quite explosive, with consecutive appreciations of the independent variable leading to larger and larger increases in the dependent variable. So let's see how well the exponential regression models our relationship between GDP per capita and capital per worker. We apply the Linus function, plug in the transformed y, so log GDP per capita, log y, and the linear non-transformed capital per worker, 1 for the constant and for additional statistics, and we enforce our regression. We can see that our r squared has reduced quite a bit, now it's 0.65, meaning that the exponential model has way worse fit to the data. We can see here as well that our slope is very small in terms of its value. That is because this is a relative change that every additional dollar of capital per worker increases your real GDP per capita by. So every dollar of additional capital per worker increases GDP per capita by 8/10,000 of a percent. So 8/10,000ths of a percent. Again, the interpretation here can be quite challenging, especially given the fact that, for example, the constant is no longer interpretable on its own, but rather it's this multiplier in front, basically, that allows us to see what is the expected real GDP per capita for a country with 0 capital endowment per worker, because if x is 0, this term collapses to be 1. So basically, the expected value of real GDP per capita of a country with 0 capital in an exponential regression is the exponent of our intercept, and it equals $5,169. So it's quite higher than the one that we estimated for our linear regression. Again, here we see quite a lower degree of fit, given that the r squared is lower, but it should not discourage us from applying further functional forms in further regression models. So for the logarithmic regression, we do the other way around. We take the logarithm of x, or our independent variable, our capital per worker, and we leave y as it is. This allows us to model relative changes in x, or percentage changes in x, leading to unit changes in y. And this is useful for modeling relationships that reach some point of saturation quite quickly, as larger and larger increases in x are needed to lead to the same increases in y. For example, capital per worker will need to double each time to increase your real GDP per capita by the same amount, say $1,000. And you can see that this would lead this relationship to reach some point of saturation quite quickly. And this is where the logarithmic regression or the lin-log form, as you leave y linear and transform x, shines if you model these sorts of relationships. So let's apply it here. Let's apply the Linus function, plug in our untransformed y, so GDP per capita, and logarithm of capital per worker. And we input one for constant, one for additional statistics, and enforce the regression. What we can see here is that the coefficients are quite larger in magnitude, whereas the r² is the lowest we have observed so far. So the degree of fit is even worse than in the exponential regression. Here, what is also important is that we cannot model the expected real GDP per capita for a country that has 0 capital endowment, because that would lead to a logarithm of 0 having to be calculated, which is tending to negative infinity. So basically, the logarithmic regression implicitly assumes that you have got a relationship such that 0 value of x is associated with a value of y approaching negative infinity. Sometimes it is sensible, but here, arguably, it's not very interpretative. And this is why, for example, our intercept is a very large negative number. Finally, if we are looking at the power law regression or the log-log form, where you take logarithms of both sides, what is quite important here is that if you try to express y in terms of x, you'll get a power law relationship with the slope, b, in this case, being the exponent of x, so x to the power of b. What that naturally models is that if x is 0, y is also 0, or it's expected to be 0, due to the fact that, well, in our case, 0 capital leading to 0 amount of goods being produced is quite a reasonable assumption. This power law model can be arguably used quite well from a theoretical standpoint. So let's apply it and plug in transformed, so log GDP per capita and log capital per worker. 1, 1 for the constant additional statistics, and we enforce it with enter. And we see that our coefficient is 0.79, 0.8 approximately, which means that we can model it as relative changes in x leading to relative changes in y. So let's say 1% increase in capital endowment would increase GDP per capita by 0.8%. And this interpretation is, again, quite intuitive, and it is quite useful when modeling particular relationships where relative changes lead to relative changes and unit changes are less meaningful to talk about. Now, let's compare the r². We can see that for the power law, the r² is much higher. The r² is quite a bit higher at 0.89 compared to 0.87, meaning that the power law regression arguably has a better fit of our data. However, here we have to discuss some implications functional forms have for the blue assumptions, which is best linear and biased estimator properties of OLS when assumptions are fulfilled. Because we are modeling the logarithm of y and not y, the property of unbiasedness, for example, is fulfilled for the logarithm of y and not y, which can be quite crucial for forecasting. Sometimes you want to forecast y in an unbiased way, and sometimes you want to forecast the logarithm of y in an unbiased way, so you should keep in mind when choosing between various functional forms. We'll evaluate the implications of functional forms for forecasting in just a bit, but first let's evaluate statistical significance of our coefficients by dividing the coefficients by the respective standard errors for both intercepts and slopes across all 4 functional forms, and evaluate them for significance using a two-tailed t-distribution, plugging in the absolute value of the t-stat we just calculated, and the degrees of freedom is always 178, as we have got the same sample and we have the same number of degrees of freedom reduction, so we can leave it as 178 throughout. And we see that all of our coefficients are statistically significant at 1%, most importantly the slopes are over here. However, the highest level of significance is again associated with the power law, with the t-stat being slightly higher than the one from the linear model. Again, that vouches in favor of the power law regression. Now, let's estimate what are the expected values of GDP per capita for a given value of capital per worker, let's say 100,000, for all four models. So for the linear model, the forecast is quite simple. It's just the intercept plus capital per worker times the slope, so around 21,000. For the exponential regression, we have to take the exponent of our exponential intercept plus our exponential slope times capital per worker, and that leaves us with only $12,000. Again, the difference between those two forecasts is quite massive. Again, it's almost half of what the linear model predicted. For the logarithmic model, we need to add intercept plus the slope times the logarithm of our capital per worker. That gives us around 30,000, so again, quite a bit higher than the linear forecast by half. So we can see that the differences are in both. We can see the differences are quite substantial, and they go in both directions if the linear forecast is concerned. And for the power law, we just have to take the exponent of the intercept and multiply it by capital per worker to the power of 0.79 of the slope. And that provides us with a forecast that's quite close, actually, to what the linear model suggested. If we consider different values of capital per worker, say if we plug in 1,000, then the logarithmic forecast would be nonsensical, the exponential forecast will be quite high, the linear forecast will be a little bit low, and the power law forecast will be even lower still, yet still meaningful, still positive. Whereas if we plug in something large, let's say 10 million, then we would have the exponential forecast being unrealistically large. Here it would be equal to a very large number due to the exponential process. Again, it's explosive. The same unit changes in the dependent variable lead to higher and higher relative changes in y, and therefore for high values of capital per worker here, the forecast of the exponential model is quite unreliable. So we're back to where we started with a forecast at 100,000. And now let's evaluate it graphically. Here we see the power law trend line being fitted across our data, and we see that the slope is exactly the same, 0.7976. The term in front of it is different than this one, but remember we have to raise e to the power of the intercept to get this term, and if we do that, we obtain exactly the same value, 2.2035. But what is interesting is the r squared. Here it's 0.86, and in our linest calculation we had 0.89. This is due to the difference between modeling y or modeling log of y. The power law regression explains 89% of variation in log y, but only 86% of variation in y itself. So if we just care about explaining y itself, a linear model would be better. However, here you have to make an informed decision based on the properties of your data and on the purposes for which you are performing this analysis in the first place. And if we try to change our trend line, and let's say go for a linear model, we'll get exactly the same result as in linest, and the fit would be quite good. If we take the logarithmic fit, we'll see that the relationship levels off quite a bit faster than we would expect. Again, for countries with high level of capital per worker, the logarithmic line underestimated quite a bit, which implies that the logarithmic relationship levels off way faster than our data, so it's not really applicable to this particular case. Whereas for the exponential regression, it's the other way around. This explodes way faster than the data shows. So basically it overestimates GDP per capita for high levels of capital per worker, and therefore this regression is perhaps not appropriate for our data set, and we stick with either linear or the power law. But again, which of those models is the best depends on the nature of your data. What is also quite interesting is that if we change our axes to be logarithmic, the power law regression would look like a straight line, because it is in those logarithmic scales. And this is another way on how to use visualization to think about which functional form is the most appropriate. Try to change your axes and see when does your cloud of points, your scatter plot, look the most linear, has the least amount of outliers, and looks the most well behaved. And that perhaps is the functional form that you would end up using. If you need to change just one of the lines or one of the axes to logarithmic to make it look linear, then perhaps the exponential or the logarithmic regression is the answer, depending on which of the axes you ended up changing. If you need to change both, then probably you have to stick with the power law, as we sort of do here. Whereas if it looks just fine as it is, then linear regression, good old lin-lin form, is the way to go. And that's all there is about choosing an appropriate functional form for your regression model, and for how to use the power of maths, particularly logarithms, to model way more with your ordinary least squares than you probably imagined previously. Please leave a like on this video if you found it helpful. In the comments below, I'm making any further suggestions for videos in business, finance, or economics you'd like me to record. And please don't forget to subscribe to our channel because it supports on Patreon. Thank you very much, and stay tuned.